doctoral fellow in biostatistics at Johns Hopkins. So Dr. Holly James works on the design and analysis of vaccine studies with a particular focus on HIV prevention and vaccine science. She also develops and applies statistical methodology for evaluating biomarkers for risk prediction and optimizing treatment strategies. Among many other projects, Dr. James is co-principal investigator of the HIV Vaccine Trials Network, HVTN, Statistics and Data Management Center at the Fred Hutch. The center provides data management and statistical bioinformatical design and analysis for HVTN studies. Last year, the center pivoted from HIV vaccine research to focus its expertise on the COVID-19 vaccine effort. So I should say that if you have questions, please put them in the chat. Most likely we'll go through them at the end of the lecture when we'll have an extended Q&A session. And now, yeah, Holly, the floor is all yours.
I'm happy to take off the mask. I'll follow suit. Super awesome. And we'll look forward to this. Okay, how am I minimizing this? All right. At first, I just want to say how just thrilling it is to be in the room with all of you and to join all of you on Zoom. If you don't get anything else out of today, I hope you spend a good deal of time interacting with people after the talk and just celebrating, spending some time together, something we've all missed very much. Okay. And do without it. All right. So I want to just flash up, people who I'm really appreciative. Just wonderful, brilliant, engaging people who I've been lucky to speak with over the past months, a year or more, or who really led some of the science that I'll be talking about today, and who have in some way have contributed some of their ideas to this talk. But of course, any errors and omissions are mine, and I'm really taking a bit of a risk here and commenting on studies that are not studies that I've owned, but I'm really going to try to articulate some lessons that I take from those studies and hopefully generate some discussion here if we have time at the end. So I wanted to just place this in the context, I think the context that we're all thinking of that underlies much of our thinking these days is, of course, the ongoing pandemic, which, just has had such a fundamental, dramatic impact on our research, on our way of life, and on our public health, with nearing, 1 million deaths in the US, 6 million globally, just staggering figures. Kaiser Health Foundation recently estimated that COVID is now the second leading cause of death in the US as of last month. And but in this context, there's been such a dramatic contribution of clinical trials and clinical trialists. And the context that I'm most familiar with is the deep contribution of those of us working in vaccines, with now 3 highly effective COVID vaccines licensed or authorized in the US, an additional 7 authorized by the WHO globally, and a staggering 65% of the global population now having received at least 1 dose of COVID-19 vaccines. Still tremendous ways to go, but really a staggering impact that we've had on global public health. But I guess what I also wanted to highlight is the opportunity that I see here, which is, in the conversations that I've had with folks over the last couple of years, and importantly with the students that I was really lucky enough to be able to engage with at the university over the last year, I think a renewed interest in clinical trials and in public health science and in population science. I've just seen a lot of enthusiasm, curiosity engendered by the COVID pandemic, and the leadership that UW and Hutch biostatistics community has played in this science that really, I think, has just re-energized, and I hope will continue to draw brilliant young scientists into this field and improve it going forward. So I wanted to frame this talk around what I see as a theme in clinical trials these days, which is the notion of augmenting randomized controlled trials with observational data. And this might be done for a variety of reasons. This is not an exhaustive list. These are the reasons that I've seen come up with, or that are, and oftentimes the most compelling reasons that this is put forward. One is to collect additional data on both the interventions and the control condition of the randomized trial, to perhaps increase or evaluate generalizability of the clinical trial results to a broader population, perhaps to improve power of the study, to study rarer endpoints or to look at specific subgroups of the population. A specific issue with decrements in power is anticipating that the control condition of the randomized trial might be lost over the course of the trial, perhaps due to evolution in the standard of care. And another important context is to collect data on a control that is not included, a control condition that is not included in the randomized trial. And so what I'm going to comment on today, or try to frame the discussion around, is the first two of these kind of buckets or motivations for collecting clinical trial data. The third is fundamentally a more challenging context, but perhaps we can have some discussion on that, and some of the comments I'll make have application to that context. But then to further frame this, I wanted to talk about sort of one dimension or way of categorizing types of control of observational data that might augment a randomized trial. One way to group these data types is to look at how they align in calendar time with regard to the randomized controlled trial in blue on the bottom there. So one fundamental distinction I want to make is between observational databases or studies that are misaligned with the randomized trial in calendar time, and they're based on historical data or historical studies, versus observational studies that are aligned or concurrent in calendar time with the randomized trial. And I want to focus on those that are concurrent in calendar time. But those might be studies that are external to the trial, that are based on sourcing data from external sources, or they might be based on data collected from an observational cohort that is within the framework and the machinery of the randomized trial. And what I mean by observational data here is quite broad. So this could be in the form of an observational cohort that's run in parallel with the randomized trial, like the first example of the WHI that we'll look at first. But they could also alternatively be drawing in data from other data sources in a given clinical context, such as registry data, surveillance data, or what some have termed these days real world data from electronic health records and the such. So I want to highlight, in my view, this is sort of a hot topic in statistics these days. We just had a seminar here at the Hutch just this week on this topic. There are folks in this department and in the Seattle biostatistics community that are working in this area. Here are some of the terms that people use for this: data integration, research synthesis, mixed randomized trials, augmented randomized trials. I think of these areas of statistical science as all related to this topic of integrating data sources with randomized trials. So what I wanted to try to do was to take really four specific randomized trials, each of which had some element of an observational study, and talk about those examples, what was learned from them, and try to thread a story and articulate some lessons learned from these trials, and pose some points for discussion at the end. So I'm going to start with the Women's Health Initiative, not just because this is the Prentice lecture, but because it is such a gorgeous and beautiful example of how to do this well. I think it's probably the gold standard of how to do this. And so it seems like a great place to start. And this was, of course, a study with key leadership played by UW folks, Ross Prentice and Garnet Anderson, both of whom were generous enough to spend some of their time helping me make sure that I understood this example. Although, again, the mistakes are mine. This was, for any of you who have not heard this story told, it was such a landmark study of health in general of postmenopausal women. It was initiated back in 1991. It's still going strong today with lots of science still to be learned. It was a complex study of 3 overlapping randomized trials augmented with an observational study. And the part of it that I want to talk about is the hormone therapy trial component of it, which consisted of over 27,000 women in the US aged 50 to 79 who were randomized to hormone replacement therapy or placebo with a regimen that depended on whether they had an intact uterus at baseline of the trial, estrogen plus progestin if they had an intact uterus, and estrogen alone if not. And then an important element that for our discussion is that women who were currently on hormone therapy but declined to discontinue it at the initiation of the trial, or who were otherwise unwilling to be randomized or ineligible for the trial, were eligible for enrollment into the observational cohort and were followed, for essentially the same endpoints as the randomized trial participants. And the primary endpoint of the trial was coronary heart disease, with the leading hypothesis going into the study based on a huge body of observational evidence was that hormone replacement therapy reduced the risk of coronary heart disease while potentially increasing the risk of invasive breast cancer. But importantly, this was not definitively established at the time. Not only was it based on observational data, but as Ross educated me, it was based on largely data on women for estrogen alone, based on observational studies where historical use of hormone replacement therapy was not carefully captured, and based on women who had relatively short durations of use, younger women. And so the longer term profile in terms of risks and benefits, and the comprehensive profile of risks and benefits in terms of the number of health outcomes that could be influenced by this therapy were not well established, and thus the motivation for the trial. And the aspect that is of interest to us today is this observational study that was run in parallel with the trial. As stipulated in the original design, it was included to assess, to essentially do sort of exploratory research and generate science understanding new risk indicators and biomarkers of disease in this cohort of women, in a large prospective cohort of older women. But it was also seen to be a resource efficient augmentation of the trial design. It was known that there were going to need to be a lot of women screened in order to enroll into this randomized trial. And this was a relatively resource efficient way to gather data on this large number of women who were going to screen out of the trial. And ultimately, one of the lessons that I want to articulate here is the science that was learned with inclusion of the observational study by helping to reconcile the randomized trial results with this enormous body of observational literature going into the study. And in terms of the design of the observational study, important elements were that it was recruiting from the same catchment area as the randomized trial, over the same calendar time period, same duration of follow-up, and essentially reasonably well harmonized data collection, essentially the same common major elements in terms of data collection, with, again, importantly, really careful data collection in terms of this observational cohort, many of whom were already on hormone therapy at enrollment, careful collection of their history and duration of hormone therapy use going into the study. But ultimately, this was a randomized trial. So the interim monitoring and the primary analysis were based on the randomized trial alone. So the findings of this is the initial findings of the estrogen plus progestin trial. It was stopped early based on evidence of not just increased risk of breast cancer, but actually an increased risk of coronary heart disease, overturning decades of observational studies pointing to a potential decreased risk of coronary heart disease. And this was based on an average of 5.2 years follow-up on the women in this study. You can see here on the right-hand side of the slide the multitude of secondary outcomes that were studied to really, again, comprehensively get a picture of the risks and benefits of this intervention, with the ultimate conclusion here that the risks outweighed the benefits. That based on this global index, there was a global index that looked at a multitude of health outcomes shown on this slide. The estimate was of an increase of an additional 19 events per 10,000 person years attributable to this intervention. So again, this was groundbreaking in the sense that it overturned decades of research. It had immediate impact on public health regulatory authorities. Prescriptions of hormone therapy use plunged by over 80%. The US FDA and other regulatory agencies essentially immediately changed the labeling for these interventions, and a dramatic impact. But still, it caused additional controversy, and there were a lot of fascinating papers written about trying to understand why it was that this randomized trial came up with quite a different conclusion than this enormous body of observational evidence. And I think that the inclusion of this observational study was key to help answer that question. And Ross and others in the WHI led a series of analyses that looked at classes of health outcomes individually, one by one, systematically, where they looked at careful analyses, harmonized analyses across the clinical trial and the observational study to help disentangle this. And here's a set of analyses that were done looking at cardiovascular outcomes, where they looked at analyses based on the estrogen plus progestin trial on the left and the observational study on the right. And as was the case going into this study, the trial estimated an estimated increased risk of cardiovascular outcomes, whereas the observational data suggested not an increase, perhaps a null effect, with confidence intervals that included 1, except perhaps for venous thromboembolism. So it's an apparent discrepancy between the conclusions based on the randomized trial and the observational study. But then based on this series of very careful analyses, considering potential confounders, that were collected systematically in both the clinical trial and the observational study, and that could be adjusted for using harmonized analyses, and importantly, stratifying here by a key effect modifier, which was the duration of hormone therapy use. Essentially, the results were able to be reconciled. And so specifically, what was seen here is that it was likely that this absence of an increase in risk in the observational study was probably attributable to the fact that the observational study was enriched with women who had a longer duration of hormone therapy use relative to women who were included in the randomized trial, and a longer duration of use was the increase in risk was concentrated in women who had recently initiated the therapy. So you can see that based on these stratified analyses, there's reasonable harmonization with regard to the conclusions that one draws from this study. And a similar sort of exercise was done looking at breast cancer. Again, initially looking at analyses in the randomized trial versus the observational study. Here, in fact, the estimated increase in breast cancer was actually higher in the observational study than in the randomized trial, until one took careful account of potential confounders and also time-varying effect modifiers in this setting. So it was determined that an important covariate was not just duration of hormone therapy use, but when it was initiated relative to the onset of menopause. And so when this analysis was stratified by duration of use and also adjusted for this gap time, the time that elapsed between the onset of menopause and the initiation of hormone therapy, the results were reasonably similar between the two populations, and could be reconciled. So not only did this help, as I understand it, really help explain the results to the community, but it really helped to articulate the nature of the effect of this intervention in a way that probably or possibly wouldn't have been possible just based on the randomized trial alone. So the next example that I want to talk about is in the context of Ebola. And this is thanks to Tom Fleming, Lori Dodd, Mike Rochen, who really played key leadership roles in this context. Tom Fleming was the chair of the DSMB of the two studies that I'll talk about. Lori and Mike were the lead statisticians for these studies. So the context here is very different. So this is in the context of Ebola. The world's second largest outbreak of Ebola occurred in 2018 in the Democratic Republic of Congo. It lasted about 2 years. This is an extraordinary lethal disease. There were about 3,400 cases over the course of this outbreak, and a 66% mortality rate. At the time, what was known in terms of therapeutics for Ebola was that there was this monoclonal antibody cocktail called ZMapp that was likely effective at reducing mortality, although that was not definitive because the placebo-controlled trial to evaluate this therapy had been underway in the previous outbreak in West Africa and had been stopped early because of declining incidence. So it wasn't providing definitive results. Meanwhile, the WHO, anticipating, anticipating this next outbreak, had put together this R&D blueprint working group, including Tom and Lori and many other leaders in the statistical science community, that had generated some consensus that in the event of a next outbreak, that the leading candidate interventions for Ebola should be studied in a randomized controlled trial. And that was articulated in a series of papers cited at the bottom here. And further motivation was provided by a really awesome meta-analysis that Lori Dodd, who is a UW alumni and now at NIA, did, that she looked at the data from the multiple studies that were done in the context of the previous outbreak in West Africa. And she compared the control groups for these various studies here. There are 6 different control groups on the left, and she compared them in terms of their observed mortality rates. And she found a wildly discrepant mortality rate across the control arms of these various studies. And she asked the question, well, so could you ever account for that using covariates and statistical analysis. If I did a statistical analysis and I adjusted for the measured covariates, which are not very many in this outbreak context, she adjusted for age, gender, and viral load at the time of diagnosis, could I then reconcile and align these mortality rates, perhaps supporting that in a future outbreak, we don't need a randomized control group, but we could adjust and get a comparable control group with statistical analysis. And she found that no, you couldn't, even with a covariate adjusted analysis, you still had wildly discrepant mortality rates. So this was further, motivation for the imperative of randomization in this context. Meanwhile, WHO had also during this time created this or created consensus around an ethical framework for the provision of experimental interventions outside clinical trials in outbreak settings with high mortality, called the MURI program. And a key element of this program, in addition to there being a number of conditions under which it might apply, a key element was that the use of that intervention be monitored and documented, and with results disseminated to the scientific community in a timely fashion. And in May 2018, at the beginning of this West African outbreak, of this Democratic Republic of Congo outbreak, the WHO convened a working group to say, is this now the time? Is this appropriate? Do we have candidate interventions that could be provided in this compassionate use context? And the panel affirmed that yes, we had a series of interventions that could be provided in that compassionate use context. But they affirmed that there was this imperative to ultimately move towards a randomized trial to definitively evaluate those interventions. And they also agreed that a benefit of providing these interventions in a compassionate use context would be actually setting up and poising the community and the sites to begin the randomized trial, that they would be able to develop their infrastructure, and in particular, cold chain distribution systems that would be required for some of these therapies, and set themselves up to be able to enroll trial participants, collect outcomes on them, monitor them clinically, that providing these interventions through the compassionate use observational context would accelerate that process of setting up the randomized trial. So in August 2018, they provided the first therapies through this compassionate use program. And there was a randomized trial that was designed, along the lines of what was, agreed upon and the consensus of the community. It was a four-arm, a randomized trial, randomizing patients in a 1:1:1:1 ratio to the active control, the most plausibly effective therapy at the time, versus an antiviral remdesivir, another antibody cocktail by Regeneron, and NAB-114, a single monoclonal antibody. And again, Lori Dodd and Mike Rochan were the lead statisticians for this study. But importantly, the important element of this design is that all four of these interventions were at the same time being provided in this compassionate use way in the community while this trial was in planning and as it started to enroll. The primary endpoint was 28-day mortality, and the agreement between all the folks involved in this was that when the clinical trial opened at a given site, the patients would then be enrolled into the clinical trial. They would no longer be in the observational study. They would only enroll to the clinical trial. But because of the staggered, entry of these clinical trial sites, what that effectively generated was an observational study leading into the randomized trial that actually partially overlapped with the randomized trial in time and in space, and generated data on the same four interventions with the same outcome. So you can perhaps see where I'm going with this, which is that there were complex issues that were encountered here around data sharing and data access and oversight of these two studies as this was going on, especially in the context where of this highly lethal disease. And I neglected to mention that this was in the context of a civil war that was ongoing in the Democratic Republic of Congo at the time. Tom can speak more eloquently to this, but the way I conceive of it is that there were actually at some point in time, there became two DSMBs that were seeing the data separately for the observational study and for the randomized trial, without, as far as I understand, like a formal mechanism for sharing the data between them. But importantly, the MURI DSMB encountered really complex issues around what to do with the interim data that they were seeing. They had to balance this imperative to inform clinical practice in the context of this ongoing outbreak of a highly lethal disease, while at the same time not compromising, the integrity and the conduct of the randomized trial. And they were several months in advance of the randomized trial. So MURI started about 3 months in advance of the enrollment of the randomized trial. So, really tricky issues. There was also, this was in the context where this is a small geographic area. The sites could see things, this was a small geographic area. Again, about a third of the people involved in who were patients at some point in time in the outbreak became involved in one of these studies. So the data at the site level were actually informative, partially informative about clinical trial outcomes. Tom articulated the need for the DSMBs to be building trust with the community in order to ultimately realize the randomized trial that everybody knew needed to happen to provide definitive evidence, and how to communicate about these data in the sense, given that they were observational data. So they're not definitive data, there are loads of limitations associated with them, but nonetheless, the best data available to inform clinical practice at the time. So, the right balance seems to have been struck in the sense that the PALM trial proceeded and was a successful trial. It was fully enrolled in a timely fashion. It provided clear and definitive results. Here are the Kaplan-Meier curves showing the cumulative incidence of death over 28 days since randomization, providing pretty definitive evidence. I don't have the confidence intervals on here, but pretty definitive evidence, even given the statistical uncertainty, that the monoclonal antibody MAB 114 and the Regeneron monoclonal antibody cocktail were superior to the active control ZMapp and remdesivir in terms of estimated lower 28-day mortality rates. And there's lots of additional science and additional lessons to be learned when comparative and combined analyses of the observational program, MURI, and the RCT are done that still have yet to be published. So I'm going to transition a little bit and now talk about COVID and the COVID vaccine research, which, as many of you know, have been key roles have been played by the UW community here. I'm going to talk first about 5 U.S. government funded phase 3 COVID vaccine efficacy trials that were conducted in partnership between the COVID Prevention Network, or CoVPN, and each of the vaccine developers. So this is the Moderna, the AstraZeneca, the Janssen, the Novavax, and the Sanofi phase 3 vaccine efficacy trials. So key statistical leadership here played by Peter Gilbert here in the Hutch and Dean Fulman at NIAID, and involving many of you here in this room or here on Zoom. These trials were pretty traditional in terms of their design, importantly and appealingly, one might say. They enrolled, they were large, and they were designed to get an answer fast. They enrolled upward of 30,000 individuals who were deemed to be at appreciable risk of SARS-CoV-2 infection or COVID-19 disease, randomized in a 1-to-1 or 2-to-1 ratio to the candidate vaccine or placebo. The primary outcome, after much discussion, was COVID-19 disease, with key secondary outcomes being severe disease, seroconversion as a marker of acquisition of infection, and importantly, understanding the durability of vaccine efficacy, with many vaccines having efficacy that takes some time to ramp up and then wanes as time accrues post last vaccination. You can see here the staggered conduct of these trials with, lined up against the waves of disease in the US, with staggered enrollment of these trials and follow-up that is still continuing on each one of these trials. So they were designed to ultimately follow all participants for 2 years post-enrollment. But the issue that I want to draw out today was one of what we call deferred placebo vaccination. So once it became clear that these vaccines were highly effective, there was much discussion around what should be done. And it was determined that in the context of this pandemic and in the context when these vaccines were so highly effective, the appropriate thing to do was to offer the vaccine to the participants that originally randomized to placebo. And that was done rather quickly because these trials were designed to give fast answers. So it was done, roundabout when you had about a median of a 3 months follow-up, only 3 months follow-up on the participants enrolled in the trials. And the fashion in which this was done varied a bit from trial to trial. In some trials, it was pre-planned because those trials were a bit later in the game. In the first couple of trials, it wasn't pre-planned, but it was determined once that efficacy was seen. In all but one study, the placebo recipients were offered the study vaccine, and one of the studies they were not offered study vaccine, but they went out and got, whatever emergency use authorization vaccine was available to them in the community. But the issue that I want to focus on was that at the time when this happened, we had, a median of 3 months follow-up on participants, and the study objectives were not fully addressed. In particular, understanding the longer-term safety and efficacy of these vaccines was still a high priority and, in fact, imperative. And so there were lots of plans laid, but I want to discuss one project in particular, and it's been a pleasure of mine to be involved with Mia Moore here at the Fred Hutch, Yifan Zhu, and our partners at UW. And what we planned to do was to build a counterfactual placebo. And we knew that this was going to be a very challenging task, but we felt that it was something that ought to be done. And we felt like among the people who could do it, we were probably the best poised to do it the best way possible, even though it was a highly challenging task. And so this is a schematic of the kind of framework that we set up for doing this. We built a partnership with IHME at UW, who draws in publicly available data that is available throughout the US as well as globally, that captures whatever a given geographic locale captures in terms of COVID-19 disease detecting COVID-19 disease cases, hospitalizations, and deaths attributable to COVID. It also draws in whatever is available in terms of seropositivity surveys, excess mortality rates, and based on this kind of bucket of data and quite geographically heterogeneous bucket of data with differences across jurisdictions in terms of what is reported, calculates using a complex statistical model what the incidence of COVID is in the I will take a sip. Count on Ruth to always be observant of what people are experiencing. Thank you, Ruth. So they calculate the incidence of COVID in the population, but we asked them to go even beyond that and calculate a counterfactual. What is the incidence in an unvaccinated population? Because this was what we wanted as our contrast for our vaccine trial. We wanted a counterfactual placebo. So they did that using a compartmental model. And that gave us, over the course of the follow-up for each of our phase 3 trials at the site level, a profile of what the incidence in that county is for an unvaccinated population over the course of the trial. Then Mia built yet another model that takes that population model and tries to calibrate it to the trial population, taking into account the individual level characteristics of the trial participants. Perhaps most importantly is the baseline serostatus of the enrolled participants, with the majority of participants being seronegative at enrollment, to try to adjust that and get it even closer to a true placebo. And then, this is probably the most unique part of what we did, which is this was Yifan Zhu's work. He fit a regression model. So we have a period of time during which we have an observed placebo incidence for the trial. So we could estimate what we call the offset. How far off is this model predicted or model-based estimate of incidence from the observed incidence in the placebo arm of the trial? And having estimated that offset, under the assumption that that offset is constant, we extrapolate forward, given an estimate of model-based incidence, we adjust it by the offset to get a counterfactual for a future period of time where we don't have an observed placebo. So first, just to articulate using a nice figure that Mia provided me using data from King County, Washington, what the raw data look like relative to the model estimates. This is data for King County, Washington. You can see the daily counts of COVID per 100 person year, 1,000 person years on the x-axis there. And then the IHME model-based estimates of population incidence in blue, which track in terms of pattern the COVID, the observed data, but which are higher, attributable to undetected COVID cases, and which also attempt to take into account the artifacts, the errors, the gaps, the messiness in the raw data, which are pervasive and differ from geographic location to geographic location. Also attempt to take into account that what you get over time in terms of raw data has trends. What we get, unfortunately, over time This is not data that's collected for research purposes. What we get over time has trends associated with it in terms of what a given geographic jurisdiction decides to report, has trends in terms of how much testing available there is in the community and what fraction of the actual cases are detected, and what the availability of testing is, and also is influenced by accruing population immunity over time. And then overlaid on this plot further, you can see the estimated placebo or estimated COVID incidence in an unvaccinated population from the IHME model, which you can see tracks reasonably well with the population incidence until about mid to late 2021, when they begin to separate, attributable to the fact that an increasing proportion of the population is now unvaccinated. And so the population incidence is different from the incidence in an unvaccinated population. So that's kind of the data that we're pulling into this. And then on the left-hand side here, we see how well this works for one of our trials. So here I'm just showing you data for one of our studies and just the placebo arm. So the pink curve is the observed placebo group incidence on a monthly basis for the period of time where we have the placebo arm followed and adequate follow-up in the placebo arm to estimate that incidence. The yellow line is the estimated incidence for an unvaccinated population based on the model. And you can see that this model counterintuitively or unexpectedly, to my view, actually dramatically underestimates the incidence in this population, at least for the first couple of months, and then they get a bit closer together. And then if we use our techniques to estimate a constant offset, adjust this model-based incidence upward, we get the blue curve. That's our estimate of counterfactual placebo incidence. And then we extrapolate that forward to the points in time where we no longer have the observed placebo group follow-up. So we wanted to do this because we felt like we wanted to attempt to articulate the many assumptions and limitations of this method. And because we had data to validate how well it works. Because we had the individual level placebo arm data for the blinded follow-up period. So obviously these models codify numerous assumptions about SARS-CoV-2 transmission, COVID-19 disease, even codifying assumptions about indirect effects of vaccination. And they're valid under this very strong assumption that offset, the discrepancy between what's observed and what's modeled, is constant over time. And we try to relax that a bit by allowing for that offset to differ by strata defined by geography and demographics, but still a strong assumption. And we can evaluate that assumption over the period of time where we have the placebo-controlled follow-up, and we can compare the two, but it's obviously an untestable assumption for future points in time. What we didn't anticipate when we started this to set up this machinery was what was going to happen with the viral variants and the rapid emergence of these new viral variants. And you can see in this figure, from the Next Strain platform that Trevor Bedford has created, the beautiful, description of how rapidly these new variants emerged. This is in the US. And overlaid with that is the timelines of these trials. So unfortunately, what you see is that round about the time where we lost the placebo arms from those trials was when, these new variants broke out and took over. And so unfortunately, a major limitation of this work is that we're estimating this offset and doing all this modeling in a period of time where we have essentially the wild type variant, and we're extrapolating it to a period of time where we have now these new variants. And that's, a pretty strong assumption to be making, that this discrepancy between the model and the observed data is not only constant over time, but constant across variants. Given enough data, we could possibly relax that assumption, but really this is, fundamentally just a major limitation of this work, and has some lessons learned in terms of trying to do this based on sort of the data, the massive amount of data that is out there that is potentially useful, but has fundamental challenges. So I think ultimately, in order to draw definitive conclusions here, we're going to need to triangulate our estimates with estimates that come from other approaches that make different kinds of constancy assumptions and that leverage different data sources to really look for consistency and get some reliable conclusions. So the last example I want to draw from is another CoVPN study. This is CoVPN 3006. This study initiated about 9 months after the first phase 3 trial studies initiated in about March 2021. This was right about when we started to get some access to COVID vaccines in the general population, in the general community. And we thought at the time, that we could roll out this study in young adults who did not yet have general access to study vaccine, who were healthy young adults who are not at high risk of severe disease associated with SARS-CoV-2 infection. So this was a study specifically trying to drill into an unanswered question that was left open from the phase 3 trials, which is how well do COVID-19 vaccines prevent onward transmission of infection. The primary endpoints were acquisition of infection, viral load, which is thought to be a good proxy of transmissibility.
She's the cool stuff, so she's talking about the cool stuff.
Oh. and we also attempted to capture actual onward transmission of infection to contacts, which I won't discuss, which is indicated in the bottom of the slide. But the element of the design that I want to drill into is that we started the trial as a randomized controlled trial. So individuals who were not vaccinated were randomized to receive immediate vaccination with the Moderna vaccine or effectively delayed vaccination. We called it standard of care because they, of course, we knew that they would increasingly have access to vaccine in the community outside the study. But through the study, they would get vaccine at the end of a 4-month follow-up period. And then, the co-chairs are listed in the bottom of the slide, and the co-lead statistician, along with myself, is Elizabeth Brown at the UW, who I'm sure is on the phone today. So schematically, the design, we were trying to achieve something similar to WHI. We had a randomized trial, and when we saw that the vaccines were more rapidly rolling out in the community than was anticipated, and given a number of delays, unfortunately, in the start of this trial, we became concerned that we would begin to lose massive amounts of information from the control arm.
I'm not exaggerating. It was like this tall.
We need to mute the phones. He joins. So we were concerned about loss of information from the control arm. So we added a an observational element to the design, an observational cohort, where the idea was that individuals who came into the sites who were not willing to be randomized or who actually preferred not to be vaccinated at that point in time could be enrolled into an observational cohort. They were recruited from the same study sites, followed over the same calendar time period, important for a highly dynamic pathogen, and had identical study procedures. And the idea was, even though we understood that this observational cohort was very unlikely to be comparable to the randomized participants in terms of outcomes that are influenced by behavior, like acquisition of infection, we thought that for pure biological endpoints like viral load and perhaps genotypic characteristics of the infecting virus, we would be able to leverage and gain information from this observational cohort. But importantly, we thought that an important element of this design is that we would have both. We would have both the randomized control group and the observational control group to check that assumption, to check how comparable those outcomes were. So in terms of the status of this study, it enrolled from March to November of 2021. And unfortunately, it was stopped early because the rollout of COVID vaccines in the community was so rapid that it eventually became very hard to recruit to this study. So ultimately, it's an underpowered study. It was designed to enroll up to 18,000 participants, and it only enrolled 1,459 randomized participants and 476 to this observational group. And the data that I'm going to show you are preliminary. There have been a number of specimen issues that have just delayed dissemination, but I think still a lot of lessons to be learned from this study in terms of this notion of augmenting trials with observational studies. And I want to acknowledge the study team. Moni, Lee, Ethan Ashby is a really awesome UW student who's been working with us, and Elizabeth. So the first really fascinating aspect of this is who is this observational cohort and how do they compare to the randomized group? And you can see, perhaps not unexpectedly, that even in a healthy young population that isn't demographically all that heterogeneous, there are quite a few striking differences between individuals who are willing to be randomized and who were not. In particular, those enrolled in the observational cohort tended more likely to be underrepresented minorities. They were in general a bit older within this young age range. They were less likely to be students, more likely to live in single family housing, and more likely to have been previously infected with this virus. But importantly, on the right-hand side of the slide also is that they had a dramatically increased frequency of self-reported risk factors for SARS-CoV-2 acquisition. They were about 2 to 4 times more likely to infrequently wear masks, social distance, more frequent attenders of large social gatherings. So perhaps that was part of why we saw a dramatically higher incidence in participants who were enrolled in this observational group, as opposed to those who were enrolled and randomized to standard of care. And importantly, this is based on analyses that censor a participant's follow-up when they receive COVID-19 vaccine. So these are all unvaccinated participants. You might think, some folks on the team thought these participants might be comparable. They're all unvaccinated, but there was a dramatic threefold higher incidence in individuals who were not being willing to be randomized versus those who were willing to be randomized, with over 20% of those not willing to be randomized having become infected or diagnosed with infection based on our procedures after about 4 months of follow-up. And this was despite evidence that we had lower adherence to the study swabbing. I neglected to say that this was an intensive study for participants. They were asked to swab their noses daily, and that's because we wanted to capture all incident SARS-CoV-2 infections and fully profile the viral load in anybody who got infected. And so that was a heavy burden to participants. There was less adherence to that in the observational group. So we're even more likely to have missed infections in the observational group. Despite that, we had a threefold higher incidence in that group. And I think ultimately, my take home is that it's unlikely that any statistical analysis can adequately adjust for the fundamental differences between these two cohorts. These are just, fundamentally different populations. But what we thought was, at least for pure biological, for pure laboratory-based endpoints, pure biological endpoints, we could leverage this observational cohort. Well, when we look at various summary measures of the viral load trajectories in the individuals who were unvaccinated, who were either enrolled in the standard care group or who were enrolled in the observational group, and who became infected. We're looking at the peak viral load, the rate of decline in viral load, the total duration of viral shedding, all potential markers of transmissibility of infection. We see quite different distributions in those viral load summary measures of those in the observational group versus those in the control group of the randomized trial. This may be due to unknown factors that we have yet to disentangle that influence your viral load, but in my mind, perhaps more likely influenced by behavior, by lower adherence to swabbing, potentially exposure to higher titers of virus. My take home from this is that even pure biological endpoints can be influenced by participant behavior. So, in summary, we've talked about these many different flavors of observational studies, and on the y-axis, in my mind, is kind of this spectrum of the extent of similarity between the randomized trial and the observational study, and it's really a spectrum. And I think these examples really help articulate that it's all the aspects of the design of the observational study and the randomized trial that influence the extent of similarity. It's the extent to which the populations overlap, both in space and time. It's the extent to which the same endpoints are collected and their method of endpoint collection. It's the extent to which we have the same covariates and their method of ascertainment. It's the duration of follow-up. But then furthermore, it's the conduct of the two studies. It's properties of the oversight. It's what's clinical, it's what sites are involved, where they're recruiting from. It's the study team, and it's even the analysis methods that are utilized that influence our ability to reconcile the results. And the necessary level of similarity, is really going to be context dependent. So, these are my take homes, and I'd love some discussion on this. I think Ross nailed it when I talked to him. This emphasizes randomized trials really matter. In the WHI example, the randomized trial was what really changed public health practice. So COVID is a perfect illustration of that. Randomized trials really matter, and that's what regulatory authorities and policymakers listen to. But their interpretation and their impact, I think these examples illustrate, can be enhanced and impacted and benefited by collecting observational data. And two ways we've seen that done here. We've seen it done in the case of WHI by looking at observational studies of ineligibles that can help generalize the results to a broader population and help reconcile the results with with external data. And then we saw it in the Ebola case that doing an observational study and a run into a randomized trial can perhaps, enhance and expedite the time to get to the randomized trial, even in an outbreak setting. And I think it could be argued that in these two contexts, arguably not collecting those observational data is an opportunity lost. But these examples also illustrate that there's a considerable work up front, planning that needs to go into doing this. You can't, in most contexts, you can't take the off-the-shelf data and make use of it. Even in the COVID example that we talked about, where we did take publicly available data, that's the basis for all this modeling. There was a lot of upfront work needed to build those relationships, get the models built, get them to estimate what we wanted. And I didn't talk even about trying to characterize the uncertainty in all those sources of information and all that estimation. And I think arguably, it could be said that for many diseases, it's unlikely that we have adequate surveillance systems in the US to really make rigorous influence based on off-the-shelf data. I think, Scott Emerson in his talk a couple of weeks ago put it well. He said, we care about data provenance. And Susan Ellenberg has said, what sets clinical trials apart is that they need to be up to their elbows in understanding data quality. And so I guess a question is, if we applied that same vigor, to collection of observational data, will we enhance the science? I think, these examples also illustrate the value of diverse study teams. In the WHI, building teams that engage folks that not just have expertise in clinical trials, but have expertise in observational data analysis. In the COVID cases, we've tried to break down the silos between the biostatistics and the math modelers. All of this should enhance our science. I think also that these examples make clear that there's no one-size-fits-all answer to when observational data are useful. It's not even specific to a trial, but it's specific to the question you're answering within that trial. But I think these examples have shown us that having both control data or having data on the same condition within the randomized control trial and outside it are valuable for checking the assumption, checking one's ability to combine the two data sources. I think the 3006 example is a fascinating illustration of, that it's really difficult to overstate the importance of human behavior, that even these pure biological readouts are influenced by a participant's willingness to comply with the study procedures to collect the specimen on which you're going to measure that biological endpoint. And so it's really a reminder of the power of blinding and randomization to control for those issues. And then the Ebola context really raises these very complex oversight and data sharing issues that arise if you're going to have a concurrent observational study and randomized trial where you have kind of real-time outcomes collected. What are you going to do with that information that you're learning from those two different data sources, and really care needed in preserving the trial integrity? One of the points that's been raised in my conversations is when one's planning these, a randomized trial that you want to augment with observational data, one of the challenges is articulating to our study teams what is the value of that observational data. And it can be quite challenging, especially when it's unclear at the design stage what the quality of the data is that you will get from the observational study. It's hard to be precise with regard to how much is it worth the investment, because adding these observational elements to a randomized trial is costly. Dave Glidden said it nicely. Are there tools for raising a red flag that the observational data are compromised or are not valid? We've seen that one tool is clearly collecting data on the same condition within the trial and outside it to check comparability. But are there other tools? I guess one final comment I have is that there's a lot of literature on this topic, as I mentioned, with these different catchphrases these days on combining randomized trials and observational data. By my read, much of this literature is focused on the issue of confounding, which is of course a fundamental issue. But there is another really fundamental issue that these examples articulate, which is the preponderance of missing variables or mismeasured variables that are typical to observational studies, and we need to deal with that too. As well as deal with the potential for confounding. Obviously, the best way to deal with that is to have a fully harmonized design that harmonizes all the data elements between the randomized trial and the observational study, but there may be place for more focus on nested two-phase validation studies within the observational study and within the randomized trial, to do that in a more resource efficient fashion. Okay, I've probably gone over, but I'd love to have some discussion. Yardi, are we gonna do that? Yeah. Stop share. Okay.
How we do
Okay.
this? Probably it's easiest if you stay there.
Okay.
Any questions from Ross Prentice? That's usually the one.
Okay. Ross is first. Over here.
Thank you. Well, thank you, Holly, for a wonderful talk. Your description of the WHI part of it was so comprehensive and accurate. You should consider yourself an honorary WHI investigator.
I'd be honored.
So it just occurred to me that, one use of these combined analysis or combined power of clinical trial and observational study is that the factors that might evolve to explain discrepancies themselves can stimulate research and substantive research. That is, the breast cancer data in the hormone therapy trial still not very fully resolved, but it's a really kind of extreme example where without any hint, say from the observational literature, even though there's a lot more literature on estrogen alone than there was on estrogen plus progestin, those the influence of estrogen plus progestin versus estrogen actually separated more with longer follow-up than the data that you showed at the end of the intervention period, and became as strongly protective for estrogen alone as strongly adverse for estrogen plus progestin. So there's something really substantial going on there. And you showed in one slide a gap time variable. So one thing you can hope to learn by having cohorts and clinical trials that have different timing characteristics, and our observation study had a lot of women that had already been on hormones for 15 or 20 years, so you get information on longer follow-up, so on. But that gap time notion, I remember sitting in my office here for a long time. I said, that has to explain it before we even did the analysis. But then my colleagues, oncology colleagues and others in the program, in spite of efforts by Garnet and myself to argue the importance of that variable, haven't really bought into it fully, somewhat, but there's a lot of other timing variables and others to investigate. But I found it interesting that some lab-based investigators and clinical investigators picked up on this in relation to their studies, particularly an investigator named Craig Jordan at MD Anderson, who pointed out that in some of the early clinical trials of advanced breast cancer, where there was little hope for an effective treatment, high-dose estrogens actually cured the cancer in about 10 or 15% of the women. And was there the 5 years that you mentioned seemed to be a critical time. If those women were more than 5 years past the menopause, they hypothesized that breast goes through an involution and then is greatly stimulated when it's exposed to estrogen, starts to divide. And that kind of a fertilizer onslaught can stimulate an immune response whereby there be latent tumor cells that haven't been recognized and apoptosis. That's at least one theory for why we see 25% or more reduction in our long-term estrogen alone trial in breast cancer incidence and intervention arm. So why doesn't estrogen plus progestin do the same thing? It has exactly the same estrogens we don't know very fully, but the progestin that was used, the MPA, medroxyprogesterone acetate, has some anti-inflammatory properties that might have offset this benefit. In fact, you get the stimulation without the immune response, and you get the opposite, a substantial increase. That increase is large, just like the other one is large when you think of restrict yourself to women that use the product for long duration and used it with good compliance and so on. So, and there's animal studies that Craig Jordan and his colleagues brought to bear to try to further this kind of theory. Still not resolved, but I think it's a really nice idea that some of our statistical analyses that are empirically based can provide leads that are either consistent with or might stimulate other kinds of analyses. So I think you're bringing together such diverse applications is a great exercise too. So I hope you'll hear more out of this, your interesting work.
Yeah, cool. Thanks. Thanks.
Thanks for coming, everybody.
Yeah.
Really appreciate this series. Tom Fleming started, I'm not sure what I did.
Yeah, sure. Yeah. Yeah, so I'm not sure. Yeah, so I'll comment a little bit on the observational studies. I think I guess the comment that I want to make is the limitations of those observations. You know, Elizabeth and I spent a long time looking at these observational studies for understand the validity with which they have estimated the COVID vaccine effects on acquisition of infection. You know, because we wanted to understand that to advocate for our science, and and I think a lesser appreciated element of those studies is, you know, they're based on captured infections in a population that has you know, a certain surveillance system and strategy for testing people. And it's not longitudinal testing of people most often. You know, it's based on people getting prompted to get tested based on possible exposures or workplace situations or symptoms. And you know, so that infrequent testing or event prompted testing has great potential to provide biased estimates of vaccine effects on acquisition. And perhaps one important way is by lower likelihood of capturing infections among vaccinated individuals, because they either don't have symptoms or they're short duration, and so they're not captured using this infrequent testing. So that's, you know, I guess just one general point that could be made in terms of, you know, understanding those data. You know, ideally we would have, you know, data from you know, settings where we've systematically and routinely tested people without waiting for a prompt to occur, and done it quite frequently, which was what we were trying to do in the 3006 study. All right, what's the other? Yeah. Yeah, social behavioral factors, confounding factors. Yeah, I think the lessons still have to be learned in terms of how, you know, what does need to be measured to predict COVID. You know, it's I was talking to somebody yesterday about you know this is a different exercise for different pathogens. For SARS-CoV-2, you know, you're exposed when you go to the grocery store, and you're exposed when you go to work, and during outbreaks, probably most of us are exposed. So it's very hard to figure out what are the most relevant factors to measure. I think, you know, that question still remains to be answered, how one can predict risk of exposure and acquisition infection.
Tom's got a 10.
Okay. How do I see? Okay. Do I unmute?
Just how to go on yourself.
Tom, can you unmute yourself?
Yeah. Can you hear me?
There you are. Cool. Hi, Tom.
Hey, great. Holly, thank you so much. This professorship is such a key part of one of the many legacies of Ross and bringing together the Hutch and the U. And you have been exemplary, Holly, throughout this professorship, including today's presentation. It's a great topic. I concede, I'm a huge fan of randomized trials. And you give some really good examples. And I look at the Women's Health Initiative and I look at the Ebola experiences and I say, thank goodness that we had the randomized trial component of WHI. And thank goodness that we had the PALM trial component of the Ebola. Yet you're right, there's so much enrichment that occurred through the observational component of WHI and understanding, as you say, how to link the RCT to all those observational data. And there was such an important contribution by the Murray program in infrastructure development and community trust, and ultimately in supporting and engaging in the PALM trial. So those are really great examples of where even a champion of RCTs like myself says, you're right, we get more with the collective inclusiveness of all of this. At the same time, I really like your counterfactual placebo example, which made a lot of sense to say, and you did it, I think, in an ideal way where you're going to actually predict the placebo and develop an offset. And that all makes sense until Delta comes and Omicron comes. And Delta and Omicron are impacting both population immunity as well as virulence of the VOCs, which if you don't account for those, which are now occurring later in the model, you're going to be overestimating efficacy using that model. And so it's a great example of these are really good ideas, but we really have to be careful. And it leads me to a question, and that is, as we look forward and look at other creative approaches, and we're looking at now emerging population immunity, and yet we do need to have still additional vaccines that are effective, and we need to see how they're effective, particular in parts of the world that sadly we're still not properly addressing, classically in Africa. The concept is, what about using concepts that I might call step wedge concepts, or what I call Fulman designs, as you know well, where we would do parsimonious designs, where we would randomize millions of people, 2 million people, but in a really simple way to immediate versus delay implementation in Tanzania, Sierra Leone, Mali, whatever, as a way of getting access to those countries and getting massive amounts of data in a simple way, but still having the randomization concept. Your thoughts?
I mean, I think that's the way to go. If I, so I'd like to put up my hand in support of that type of approach for regions of the world where there's not yet access to vaccine. This randomization is key, and even in the process of providing access to vaccine, doing it in a randomized fashion will provide us much more rigorous answers to that question. And as you know, Tom, there was considerable discussion in the context of the U.S. funded phase 3 trials when the boosters were added to some of these trials. Could that be done in a randomized fashion, in a step wedge type fashion? Ultimately, we didn't win that. We didn't win on that proposal, but we're trying to exploit essentially what we think is sort of pseudo-random timing of provision of boosters in the context of those phase 3 trials to do a similar type of analysis by comparing the participants who have yet to be boosted with those who have. Yeah, thanks, Tom.
Hi, I'll ask a question. Not being a clinical trials person, so with the COVID, obviously you can get a lot of people really fast, and even if you have a non-randomized, say, booster or whatever, there's sort of an urgency of the whole thing going on that you kind of have to grapple with. So, maybe a randomized trial is the perfect solution, but maybe the imperfect solution is still helpful enough to be worth pursuing. But I want to come back to, I don't know if you listened to Scott's seminar a few weeks ago, and since I work in Alzheimer's disease, we got this horrible drug that's been sort of approved, if you will. What about with the chronic diseases? The virus, you've got some things that we can predict what's going to happen. Evolutionary biology will predict that the virus is going to develop ways of getting around our defenses. So some of the things with Delta and Omicron are kind of predictable, that some of these things are going to happen. It's a simpler organism, and so on. But when we have chronic diseases, it's really, really, really hard to carry out some of these clinical trials. They don't go fast. They're really slow. And then you have the populations that want the drugs, that are battling, to get approval and so on and so forth. What are your thoughts in that setting, which is a much more difficult setting, I would say, than you've been working in?
Yeah, it's hard to comment on how feasible this is for chronic diseases. I don't consider myself an expert in those areas, but I guess I would just say, like, yeah, even for the pathogens we've been working in, infectious disease, it's still, as you can see, it's
hard.
There's still unknown modifiers or mediators of a given effect of a vaccine on an endpoint. Still tremendous variation amongst individuals in terms of their risk of acquisition, their viral load trajectories, and still tremendous temporal variation, obviously, in population dynamics. So I don't know if it's easier. Yeah, I don't know. Does anyone else want to comment on chronic?
Maybe Scott. He's listening.
Ross, Charles. Yeah, Pam.
Yeah, I will I wanted to make a comment based on this idea that I fully support large, simple trials, but in my mind, that's almost an oxymoron, because as soon as you go large, it's not simple. And from my own experience, you're either going around the world and having to deal with labs that aren't going to do the same, and custom issues, or maybe you're relying on electronic health records, and the systems are going to be changing. There's local practices and how they record data. So I think it's a great tool, but I don't know, is there such a thing as a simple large trial? And that'll be just a challenge we have to think about going forward, because it is a powerful tool, but I think it's a misnomer. Even if you're just measuring one thing, it's quite challenging. In my experience, most recently was during the COVID pandemic, and it was trials of convalescent plasma, when suddenly the incidence was crashing, and there were tens, hundreds of trials ongoing. Several trials at the leadership of Andrea Troxel at NYU, actually, before they stopped, they pulled their data with NYU, because we realized the only way any of us could get an answer was to pool. So we tried to, they came up with a large, simple, minimal data sheet that we all just start pooling. We just had to hospitalize patients and a randomization, something very simple. And we uploaded our data on an online tool. So we tried to make it as simple as possible. Just the nature of the number of institutions being around the world, the time zones, having to do the PSNP together. We've got time zones around the world. It was really, it was a rewarding experience, and I think we got a great answer, but it was not simple.
Yeah.
Statistically simple versus operational.
Yeah. I mean, obviously, there's some benefit in the trials I've trafficked in here with network structure, helping to standardize some of those elements across geographic locations and so on. But I agree. Yeah, it's still, still doesn't make for maybe simple is not the right term. Yeah. A lot of variability. Yeah, Garnet.
So Holly, thank you so much. And thank you to the whole team for all for making it work and stuff. It's just an honor to be associated as well. I'm wondering, and by the way, go ahead and use the mic.
Oh, yeah.
Let me see. And I agree with Ross, you should put this under
So I'm wondering if you have developed any thoughts about when we should be considering adding an observational component onto our randomized trials, or when we shouldn't, or maybe the reverse, which I've tried to do recently, is when I have an observational study embed a clinical trial. You thought about
Yeah, you mean, so an observational study followed sequentially by a randomized trial, or you mean, or conducting both in parallel?
Well, my example was a study was originally proposed as an observational study, and it didn't get funded. And when I got involved, I said, let's embed a clinical trial within it.
Ah, cool.
To answer that question.
Yeah.
We did get it funded, but it's raised lots of other questions. So I'm just kind of curious.
Yeah, that's fascinating. I have never come across that. Yeah, that raises lots of interesting issues. I mean, it's sort of, yeah, brings to mind the notion of validations. It's a good design inside of an observational study design. That's interesting. Yeah, I mean, I guess some of the comments I was making at the end, I was trying to get towards. I mean, I feel like it's terribly hard to provide general guidance of when to do this. It's obviously highly context dependent. But to me, it's dependent on the question one's asking, in addition to the study itself, right? So there's certainly, I mean, that's one thing we were trying to do in 3006 was, for some questions, we knew the observational study was not going to cut it, but for others, it might help us. So it's dependent on that. I mean, I do think these examples really help show how much better it is to have both, to have this internal check. Yeah. What other general guidance can we provide? I mean, things that are clearly behaviorally influenced are not good candidates for endpoints that are behaviorally influenced, not good candidates for getting value from the observational study.
I would say
Yeah.
standardized surveillance.
Yeah. Right. So it's not just, I mean, I feel like that's a bit lost in the literature. It's not just what the endpoint is, but it's how it's captured, how it's measured, how frequently, and what the prompts are for capturing it. That is really, can't be lost.
His breast cancer analysis was restricting the observational study to women who had a mammogram. That's something you might do with an observational study. Data.
Right.
That's
Right.
the WNI example makes me think that we should have enrolled the vaccine seekers from 2006 study into the observational cohort, or a different, a separate cohort as well to see.
Yeah. Yep. Yeah. Yep. All right. One more. Yeah. You did.
Oh, yeah. A short question now. Okay. Yeah. Congratulations, Holly. I think you did a great job. Really enjoyed the presentation. I think you nailed it. I was just kind of thinking, as a statistician from the data analysis perspective, I'm curious to know the role of like sensitivity analysis, like especially, for example, like tipping point analysis had played in terms of reconciling results in the RCT and observational study, and how like the regulatory agency views that type of analysis in reconciling conflicting results from the observational study and RCT. I mean, we see lots of literatures on doing that, adjusting for confounders, observed, unobserved, confounders. I mean, how is that actually being used in this kind of context?
Yeah, I mean, I wonder if that's, if any of these other studies that's come up, in WHI, if those observational data have been presented to FDA or and these analyses, what their take has been from these. Yeah, I don't know from my experience of where the kind of two sets of analyses have been presented and how FDA has reacted. I don't know if anyone else has that experience. Yeah.
I guess I would one more thing. You brought up the ethical issues that you encountered in the Ebola example. There are also logistical issues in doing this, and we encountered it in WHI, and I have in my more recent experience is recruitment. So if they're in parallel, you're asking people to choose, and
Right.
people will naturally choose an observational
Yep.
the arm if they're given that
Yep.
choice usually.
Yep.
And that so in WHI we actually did not allow enrollment into the observational study for the first year to try to get it jump started. And in my other example, the observational arm pretty much filled up. I had to say, no, we have to
Right.
close it or almost close it to get those in the randomized trial.
Right. And yeah, we encountered similar issues in the 3006 study. It was rapidly became easier to recruit to the observational cohort than the randomized trial. I remember Tom mentioning that it was a key decision and point of agreement for the Ebola context that not be the issue, that once a trial was open for the randomized, once a site was open for the randomized trial, that's where patients went. They weren't given a choice. Yeah.
That's right, Holly. So basically in that Ebola example, as the outbreak was emerging through Africa and it was spreading from Beni to Batumbo to Katwa and Mangina, as the infrastructure was developed, so there was immediate access through Murray to compassionate access to these interventions. And then the infrastructure was being built in the middle of, as you noted, a civil war. And when that structure was there was uniform consensus that when you're eligible, then you must go onto the RCT. And so people were given access, but then that while we still had equipoise, the best way to get the most reliable answers to get into the RCT, and the community did accept it.
All right. Everybody seems tired. All right.
No, that's
Thank you, everybody.